Hi, this is Dr. Weideman. I'm going to show you how to use StatCrunch to work some problems from Chapter 5. And I'm going to use some problems from the ebook, which you can find in my Stat Lab. And the first problem I'm going to work on is problem 26. And it tells us that John Beale of Stanford, California, recorded the speeds of cars driving past his home, where the speed limit read 20 miles per hour. The mean of 100 readings was 23.84, with a standard deviation of 3.56. How many standard deviations from the mean would a car going under the speed limit be? Okay, so a car going under the speed limit would be going 20 miles or less. And we don't actually need StatCrunch. We can just use a calculator to do this. So I'm going to go ahead and find the z-score for a car going 20 miles per hour. So I take the car speed of 20 minus the mean, which was 23.84, and then divide by the standard deviation, which is 3.56. So that car is about 1.08 standard deviations below the mean. And then the next question that they pose is, what would be more unusual, a car traveling 34 miles per hour or one going 10 miles per hour? So we could do this two ways. We could do z-scores. So let's go ahead and find the z-score for the car going 10. So I take that number, subtract the mean, divide by the standard deviation, and we get, somehow I made a mistake, let's try it again, 10 minus mean is 23.84, and then I want to divide by 3.56, the standard deviation. And so that car is about 3.89 standard deviations below the mean. And then the other car they asked about was a car going 34, so let's find the z-score for that. 34 minus 23.84, and divide by the standard deviation. And this car is 2.8685. So we can see, based on the z-scores, that one of the cars, the car actually going 10 miles per hour, is more unusual. We can also use some of the density tools, the little calculators in StatCrunch. So I'm going to go ahead and go over to StatCrunch, and I'm going to go to Stat Calculator Normal. And the first thing you want to do is, when you're working a problem here, put in the mean and the standard deviation. And ours was 23.84 and 3.56. And now let's talk about that car that was going 10 miles per hour. Let's find the probability, if we select one car, that it would be going less than 10 miles per hour. And there's the probability. It's pretty small. And let's go ahead and switch over and do the car that was going 34 miles per hour. And that one's a larger probability. Notice also you could just compare, let's go back to the book again, you could just compare the fact that the distance from 10 to 23.84 is further than the distance from 23.84 to 34. So obviously, even without doing much calculation, you could tell that this car would be more unusual. Okay, we're going to go on to the next page and continue with the same data. And by the way, there's a little link here to get to the data set. You can also get to it from the StatCrunch website for the textbook, and go to Chapter 5 and find the car speed data set. But let's go ahead and go to the next page in the ebook. And there's another problem that uses the same data, and it says, for the car speed data that we were just looking at, do you think it's appropriate to apply a normal model? And so I'm going to go back over to the data set and show you how to use some other tools in here. Let's go ahead and do a histogram, which we learned about earlier in the semester. And let's take a look at that histogram. And what are we looking for when we're looking for underlying normality? We're looking for a unimodal and fairly symmetric histogram. And this looks pretty good. And we also have quite a few data points. Remember, we have 100 data points, so we're not as worried about deviations from the unimodal symmetric when we have such a large sample size. We can also do a normal probability plot, which StatCrunch calls a QQ plot. And if we go ahead and select the variable speed, what we're looking for here is, when the data are plotted on that normal probability plot, we want the data points to be fairly linear, following a straight line. And StatCrunch actually superimposes that straight line so you can get an idea to assess how well the data fits. And that looks pretty good. Okay, so let's go back over to our ebook, and I want to do another problem on the next page, on page 137, and it's problem number 48. And problem 48 is dealing with tires, and they're going to work with snow tires, and they're talking about the tread life. It can be described by a normal model with a mean of 32,000 and a standard deviation of 2,500. So the first thing I'm going to do is go ahead and get that calculator opened up, and we're going to go ahead and put in the mean, which was 32,000, and the standard deviation for the snow tires was 2,500. So we're going to need it set up that way to work the problems. And the first question, it says, if you buy one of the tires, would it be reasonable for you to hope that it would last at least 40,000 miles? Okay, so what we want to know is, what's the probability that the tire lasts 40,000 miles or more? So I'm going to put 40,000 in here, and then I'm going to hit compute. And so the expectation that the tires would last at least 40,000 miles is not real, or more than 40,000, is not really likely. It's a pretty small probability. And let's go back and do the next question. Approximately what fraction of tires can be expected to last less than 30,000? Okay, so now we want a less than, and we're going to go ahead and change this to 30,000. So what proportion are expected to last less than 30,000? About 21.2%. And what fraction can be expected to last between 30 and 35,000 miles? Okay, so for this one, you're going to click on the between option here, and you want to go between 30 and 35,000. And the tool will actually compute the area and show it to you on the curve. So about 67.3% of tires are going to be expected to last between 30,000 and 35,000 miles. Estimate an IQR of the tread lives. Okay, so the IQR, remember the IQR is the middle region, middle 50%. So if I go over here, and actually what I want to find, I need to find Q1. To find Q1, I want the area that's to the left, that's 25%. And so we come up with 30,314. I'm going to go ahead and round it off. And then I want the upper bound here, so I'm going to go ahead and find the upper tail. I'm going to change this to greater than and change this here to 0.25. And so now I've got the Q3 value, and the Q3 value is 33686. And then if you remember, to find the interquartile range, we just subtract. So I take the upper bound at 33686, and I subtract the lower quartile, quartile 1, which we found to be 30314. And so my IQR is about 3,372 miles. Okay, and there's one last question on here. In planning a marketing strategy, a local tire dealer wants to offer a refund to any customer whose tires fail to meet a certain number of miles. However, he doesn't want to take too big of a risk. If he's willing to give refunds to no more than 1 out of every 25, for what mileage can he guarantee the tires to last? Okay, for the first thing we need to know is 1 divided by 25. 1 out of 25 means it's 0.04. So if I go back excuse me, to my tool, what I really want to find is what's the value such that the area over here to the left is 0.04. Okay, so that tire value would be 27,623. So if he guarantees the tires will last at least this long, or he'll replace them, that's only going to affect about 4% of the customers. So that would meet his criteria. So he would put out a guarantee that if your tires fail to last 27,623 miles, I'll give you a new set of tires. So hopefully this will help you with working problems in Chapter 5.